We begin with a number that is difficult to comprehend: 100 billion. That is the conservative estimate for the number of stars in our home galaxy, the Milky Way. For centuries, astronomers looked up at this glittering archipelago of light and assumed that we were average. This is the essence of the Copernican principle: the idea that Earth is not unique, that our Sun is a standard yellow dwarf, and that our position in the cosmos is unremarkable. By logical extension, we assumed that the architecture of our solar system, 4 small rocky worlds huddled close to the warmth, an asteroid belt divider, and 4 gas giants patrolling the frozen outer reaches, was the standard blueprint for planetary formation across the universe. We were wrong. Over the last 3 decades, we have transitioned from a species that suspected planets existed to one that knows they are everywhere. We have confirmed over 5,600 exoplanets, with thousands more candidates waiting in the data buffers. If you enjoy diving into cosmic mysteries, hit that like button and subscribe. Tell me in the comments where you are listening from, what time it is there. And as always, with our videos, the visuals are here to add context, but they aren't necessary to follow along. Thank you for always having our back. Prepare yourself and let's dive in. We now know that planetary formation is not a rare accident, but a standard byproduct of star birth. Nature makes planets with the same enthusiasm that it makes stars. But as the data began to pour in from ground-based observatories and space telescopes, a disturbing pattern emerged. The galaxy is teeming with planets, yes, but it is also teeming with chaos. We have found hot Jupiters roasting in orbits that take only days to complete. We have found super-Earths and Mini-Neptunes, planets with masses between Earth and Neptune, which appear to be the most common type of planet in the galaxy, yet our solar system possesses 0 of them. The more we look, the more isolated we appear. We are not the rule. We are the exception. This realization forces us to confront a profound scientific mystery. Is the architecture of our solar system a prerequisite for the emergence of technological life? Or is it merely a roll of the cosmic dice? To understand the gravity of this question, we must first understand exactly how strange our home really is compared to the galactic census. Let us analyze the standard model of planetary systems that has emerged from our surveys. If you were to take a random sampling of stars in the Milky Way, you would likely find systems that are tightly packed. In our solar system, the innermost planet, Mercury, orbits at a distance of about 0.39 astronomical units, AU, from the Sun, roughly 58 million kilometers. To us, this seems close, but in the context of the galaxy, the space inside Mercury's orbit is a gaping void. Statistical analysis of Kepler data suggests that roughly half of all Sun-like stars possess planets orbiting inside the distance of Mercury. We see systems with 5 or 6 planets crammed into a space smaller than Mercury's orbit, whirling around their host stars in resonance chains where their years last only a few days or weeks. This presents a stark contrast to the solar system's ordered spacing. Our system is expansive, with vast distances between the planets. Jupiter sits at 5.2 astronomical units, Saturn at 9.5 astronomical units. In many observed systems, gas giants are not found in the cold outer reaches, but have migrated inward, disrupting the orbits of any potential Earth-like worlds. This is the first major anomaly, the Kepler Dichotomy. We observe a split in the population of planetary systems. On one hand, we have the tightly packed, highly efficient systems often containing super-Earths. On the other, we have systems like ours, dynamically colder, more spread out, and possessing a specific hierarchy of rocky inner worlds and gas giant outer worlds. Current estimates suggest that perhaps only 1% to 10% of solar-type stars host a system with an architecture similar to ours. Why does this matter? It matters because density and arrangement dictate destiny. In those tightly packed systems, the gravitational interactions are intense. Planets tug on each other with ferocity, often locking into resonances that stabilize them but might preclude the stable, long-term climates necessary for biological evolution. Furthermore, the most common type of planet we find, the super-Earth, is a terrifying enigma, ranging from 1.5 to 10 times the mass of Earth. These worlds occupy a mass range that is completely absent in our system. We have the Earth, 1 Earth mass, and then a massive jump to Uranus, 14.5 Earth masses, and Neptune, 17 Earth masses. We are missing the galaxy's favorite child. The composition of these super-Earths is a subject of intense debate. Are they scaled-up rocky worlds with crushing gravity and thick atmospheres? Or are they scaled-down gas giants, sub-Neptunes, shrouded in suffocating envelopes of hydrogen and helium? If they are the latter, they are likely sterile. If they are the former, they might be geologically stagnant, lacking the plate tectonics that recycle carbon and stabilize a biosphere. The fact that our system skipped this mass category entirely is a puzzle piece that does not fit the standard model of accretion. Then there is the issue of orbital eccentricity. In our solar system, the planets orbit in nearly perfect circles. Earth's orbital eccentricity is a mere 0.016. This circularity ensures that our distance from the Sun remains relatively constant, keeping our climate stable over millions of years. However, when we measure the orbits of exoplanets, we often find high eccentricity, planets moving in elongated ovals that swing them scorching close to their star before flinging them out into the deep freeze. High eccentricity is a signature of violent gravitational histories, perhaps caused by planet-planet scattering where worlds are ejected from the system entirely, leaving the survivors in chaotic paths. Our system's circular, distinct, and orderly nature implies a history of relative calm, or a very specific type of violence that resolved itself into stability. This brings us to the galactic data drop that is currently looming over the field of astrophysics. We are standing on a precipice. Much of our current understanding comes from the Kepler Space Telescope, which used the transit method, detecting shadows, and was biased toward finding those close-in, short-period planets. It was excellent at finding the anomalies, but perhaps less effective at finding the norm, if the norm looks like us, widely spaced and slow-moving. We are currently in a waiting game for the next massive release of data from the Gaia Space Observatory. Gaia is cartographing the galaxy in a way never before attempted, monitoring the positions of over 1 billion stars with micro-arc-second precision. The question that haunts planetary scientists is whether Gaia will reveal a hidden population of solar system analogs, systems with distant Jupiters and Saturns that take decades to orbit, or if it will confirm our isolation. If Gaia looks at millions of stars and sees only silence where our Jupiter should be, the implications for the rarity of life are staggering. If the architecture of the solar system is indeed a 1 in 100 or 1 in 1,000 occurrence, we must ask what specific benefits this architecture provides. Why is it better to have a small rocky planet at 1 astronomical unit and a massive gas giant at 5 astronomical units? The answer may lie in the invisible gravitational web that connects the giant worlds to the small ones. It is not enough for a planet to be in the habitable zone, that Goldilocks region where liquid water can exist. A planet must also be protected. It must be shepherded. Consider the role of mass. The Sun contains 99.8% of the mass of the solar system. Of the remaining 0.2%, Jupiter contains more than double the mass of all the other planets combined. It is a colossus, a failed star that dominates the gravitational landscape of our neighborhood. In many other systems, we see hot Jupiters that have spiraled inward, likely obliterating any small rocky worlds in their path, like a wrecking ball through a construction site. Our Jupiter stayed put, or at least it didn't come all the way in. This stay-at-home Jupiter scenario might be the singular variable that allowed Earth to survive its infancy. As we dive deeper into this analysis, we must keep 2 numbers in our heads. The first is 11 billion, the estimated number of Earth-sized planets orbiting in the habitable zones of Sun-like stars in the Milky Way, extrapolated from Kepler data. That sounds like a lot. It sounds like a universe teeming with life. But the second number is 0. That is the number of systems we have found that possess an Earth-sized planet in the habitable zone and a Jupiter-sized planet in the outer system. Not a single one. Is this merely a failure of our current detection technology, which struggles to see distant planets? Or is the universe filled with lonely Earths that were sterilized by asteroid bombardments because they lacked a Jupiter shield? Or perhaps the universe is filled with Jupiters that destroyed their Earths long ago. The silence of the cosmos is loud, and the specific, orderly, low-entropy arrangement of our 8 worlds is the frequency we are trying to tune into. Before we can understand the future of our search for life, we must understand the mechanism that might make our existence possible. We must look at the monsters that live in the dark, the gas giants that act as the gatekeepers of biology. If you enjoy deep dives into the mechanics of the universe and want to support high-quality science communication, consider subscribing. We are peeling back the layers of a mystery that spans 2.5 million light-years of history. The collision of data and theory has already begun. To understand the fragility of life, we must look at the scars on the face of the moon. When you look up at night, you are seeing a record of violence, billions of years of cosmic debris slamming into the surface. Earth suffered the same bombardment, but our active geology and weather have erased most of the craters. However, the threat remains. We live in a shooting gallery. The solar system is littered with leftover construction material. Asteroids, comets, and centaurs that wander the dark spaces between planets. For a biosphere to evolve from simple single-celled organisms to complex intelligent life, it requires time. Billions of years of relative stability. It cannot constantly be reset by extinction-level impact events. This is where the Jupiter shield hypothesis enters the equation. Jupiter is not just a planet. It is a gravitational anchor. With a mass 318 times that of Earth, it exerts a profound influence on the architecture of the solar system. Early simulations in the 1990s suggested that without a Jupiter-sized body in the outer solar system, the flux of comets impacting Earth would be 1,000 to 10,000 times higher than it is today. Imagine the KPG extinction event, the asteroid that wiped out the non-avian dinosaurs 66 million years ago, happening every few thousand years. Civilization, let alone complex multicellular life, would never get a foothold. The mechanism is gravitational ejection. As comets from the Oort cloud or Kuiper belt fall toward the inner solar system, they must cross the orbit of Jupiter. The gas giant acts as a goalie. Its immense gravity slingshots these icy bodies out of the solar system entirely, or traps them into stable orbits where they can do no harm. This is known as the vacuum cleaner effect. For decades, this was accepted dogma in planetary science. A good Jupiter is a prerequisite for a habitable Earth. However, recent, more sophisticated simulations have added nuance to this picture, turning the shield into a double-edged sword. In some scenarios, Jupiter doesn't just deflect impactors. Its gravity can actually destabilize asteroid orbits, flinging rocks toward Earth that would have otherwise stayed harmlessly in the main belt. This revelation complicates the rare Earth equation. It suggests that it's not just about having a gas giant. It's about having a gas giant with the precise mass and orbital parameters of Jupiter. A slightly more massive Jupiter, or one with a higher eccentricity, might turn from a shield into a sniper, actively hurling debris at the inner habitable zone. This delicate balance extends beyond just deflecting rocks. We must consider the delivery of volatiles. Earth formed inside the snowline, the distance from the sun, where it was too hot for water to condense into ice. The proto-Earth was likely a dry, scorched rock. The water that fills our oceans today, the solvent for all known biology, had to be delivered. It likely arrived on the backs of icy asteroids and comets from the outer solar system. Here, Jupiter played a crucial role not as a blocker, but as a delivery man. The gravitational perturbations caused by the formation and migration of Jupiter likely scattered water-rich planetesimals inward, bombarding the young Earth and gifting it the oceans we see today. So, the requirement for life is paradoxically complex. We need a giant planet that is violent enough to throw water at us early on, but protective enough to keep the dinosaur killers away later. This specific sequence of events, delivery followed by protection, implies a highly specific orbital history. Let's contrast this with the systems we are finding elsewhere. As we noted, many exoplanetary systems feature hot Jupiters. These are gas giants that orbit extremely close to their stars, often closer than Mercury is to the Sun. These planets did not form there. The physics of accretion doesn't allow enough material to gather that close to a star to build a giant. They formed further out, like Jupiter, and then migrated inward due to drag from the protoplanetary disk or gravitational interactions with other planets. As a hot Jupiter migrates inward, it crosses the habitable zone. The result is catastrophic. Any Earth-like planets forming in that zone would be scattered, swallowed, or ejected into interstellar space. A system with a hot Jupiter is effectively a dead system for Earth-like life. The cold gas giant configuration, where the giant stays past the snowline, appears to be essential. Yet, when we look at the current data, cold Jupiters are harder to find. This is partly an observational bias, which we will discuss later, but it also hints at a physical reality. The Goldilocks scenario for gas giants seems rare. We need a giant that forms, grows large enough to dominate, but then stops migrating before it destroys the inner sanctum. We must also consider the composition of the star itself, the metallicity of a star. Astronomers speak for the abundance of elements heavier than hydrogen and helium, seems to correlate with the presence of gas giants. Stars with higher metallicity are more likely to host Jupiters. Our Sun is relatively metal-rich. This suggests that in the early universe, before generations of stars had exploded to enrich the galaxy with heavy elements, gas giants, and therefore shielding mechanisms, might have been impossible. This places a temporal constraint on when habitable systems could arise in cosmic history. Furthermore, the presence of Saturn cannot be ignored. Some dynamicists argue that it is the specific resonance between Jupiter and Saturn that prevented Jupiter from migrating all the way into the Sun. This Grand Tack Hypothesis, which we will explore in detail later, posits that Jupiter started moving inward, but then Saturn grew large enough to pull it back, locking them in a gravitational dance that retreated outward. If our solar system had only formed Jupiter and not Saturn, Earth might not exist. We might have been crushed by a hot Jupiter billions of years ago. This adds another layer to the filter. We aren't just looking for a star with a planet. We are looking for a star with a rocky planet in the habitable zone, a gas giant in the outer zone, and a second gas giant to act as a gravitational counterweight. The probability calculation involves multiplying these fractions together. If 50% of stars have planets, and 10% have gas giants, and 10% of those have the Jupiter-Saturn configuration, the numbers start to shrink rapidly. We also need to discuss the magnetic environment. While not directly a Jupiter shield issue, the interplay between a star and its planets is magnetic as well as gravitational. Gas giants possess immense magnetic fields. Jupiter's magnetosphere is the largest structure in the solar system. If it were visible to the naked eye, it would appear larger than the moon in our sky. There is speculation that the interaction between the stellar wind and a giant outer planet's magnetosphere might offer some form of protection or modulation of high-energy particles for the inner system, though this science is still in its infancy. What is clear is that the habitable zone is an insufficient metric. We have found many planets in the habitable zone of red dwarf stars, M-dwarfs, such as Proxima Centauri b and the TRAPPIST-1 planets. But M-dwarfs are violent, prone to massive stellar flares that could strip an atmosphere in days. And without a distant gas giant to stabilize the system, these planets are often tidally locked, with one face forever baking and the other forever frozen. The Sun-like star plus distant Jupiter combination remains the gold standard for a stable, long-term biosphere. The implications of the Jupiter shield hypothesis are profound. If Gaia Data Release 4 reveals that cold Jupiters are common, then the galaxy may be full of protected nurseries ready for life. But if it confirms that Jupiter-like orbits are statistical outliers, that the standard outcome is either no giant or a murderous hot Jupiter, then the rare Earth hypothesis gains massive ground. We might be living in a fortress in a galaxy of ruins. To find the truth, we had to learn how to see the invisible. We had to learn how to detect planets not by seeing them, but by watching the dead dance. This journey of discovery began in the most unlikely of places, around a stellar corpse screaming radiation into the void. Before we could search for life, we found the afterlife. The year was 1992. The hunt for exoplanets had been a graveyard of false positives and retracted claims for decades. Astronomers had reported companions around Barnard's star, 70 Ophiuchi, and others, only to have the data dissolve under scrutiny. The consensus was that finding a planet around another star was bordering on impossible with current technology. The brightness contrast was too high. The angles were too small. we were trying to spot a firefly next to a searchlight from thousands of kilometers away. Then came the anomaly. It didn't come from a sun-like star. It didn't come from an observatory looking for life. It came from the Arecibo Observatory in Puerto Rico, a massive radio telescope listening to the rhythmic ticking of a dead star. Alexander Wolszczan and Dale Frail were observing a pulsar named PSRB 1257+12, also known as Lich, located 2,300 light-years away in the constellation Virgo. A pulsar is a neutron star, the crushed core of a massive star that exploded in a supernova. These objects are terrifying in their density. Imagine a mass greater than our sun compressed into a sphere the size of Manhattan. They spin with incredible speed, emitting beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across Earth like a lighthouse. When the geometry is right, we see a pulse. Pulsars are the most accurate clocks in the universe. Their rotation is so stable that they rival atomic clocks. If a pulse arrives a fraction of a millisecond late, it means something is wrong. Wolszczan and Frail noticed exactly that. The pulses from Lich were arriving offbeat. Sometimes they were slightly early, sometimes they were slightly late. The pattern was periodic. The only explanation was physics. The pulsar was moving. It was being tugged back and forth. Something was orbiting it. By analyzing the timing variations, they calculated the presence of two bodies. These were not stars. Their masses were too low. They were planets. The first confirmed exoplanets in history were not found around a warm, yellow sun. They were found orbiting a radioactive stellar carcass spinning at 161 times per second. The system, later named Lich, is a hellscape. The two planets, Poltergeist and Phobetor, masses 4.3 and 3.9 times Earth, orbit at 0.36 and 0.46 AU. A third, moon-sized object Droger, orbits even closer. The environment is bathed in lethal X-rays and high-energy particles. The magnetic field of the pulsar is trillions of times stronger than Earth's. Any atmosphere these planets might have had would be stripped, ionized, and blasted away. Life as we know it is impossible here, but their existence was a shock to the system of astronomy. How could planets exist around a neutron star? The supernova explosion that created the pulsar should have destroyed any pre-existing planetary system. The blast wave would have incinerated inner planets and ejected outer ones. The leading theory is that these are zombie planets. They formed after the supernova. The explosion likely failed to eject all the material, or perhaps the pulsar destroyed a companion star, reducing it to a disk of debris. Out of this radioactive ash and dust, a second generation of planets coalesced. This was a profound realization. Planet formation is robust. If nature can build planets from the debris of a supernova in a high radiation environment, then surely it must be building them everywhere. This discovery shifted the paradigm. It proved that Earth-mass planets could exist. It proved that our detection methods, specifically looking for the wobble of a star, worked. In the case of the pulsar, we used pulsar timing variations. It is an incredibly sensitive method, capable of detecting asteroids, but it is limited to pulsars, which are rare and deadly. We needed a way to apply this logic to normal, living stars. The principle is simple. Gravity is a two-way street. The sun pulls on the Earth, but the Earth also pulls on the sun. They orbit a mutual center of mass, called the barycenter. Because the sun is so much more massive, the barycenter lies deep inside the sun, but not at its exact center. As the planets orbit, the Sun executes a tiny, complex dance around this point. It wobbles. If we could measure this wobble in other stars, we could infer the presence of planets. But normal stars don't pulse. We can't time them like clocks. We needed a different ruler. We needed light. We turned to the Doppler effect. When a sound source moves toward you, the sound waves compress and the pitch goes up. When it moves away, the waves stretch and the pitch goes down. The same happens with light. If a star moves toward Earth, its light shifts toward the blue end of the spectrum, blue shift. If it moves away, it shifts toward the red shift. By taking the light from a star and passing it through a spectrometer, a prism on steroids, we can break it into a rainbow. Embedded in this rainbow are dark lines, absorption lines caused by elements in the star's atmosphere absorbing specific wavelengths. These lines act as markers. If the star wobbles, these lines shift left and right. The challenge was precision. The wobble induced by a planet like Jupiter on the Sun is about 12 meters per second. That's the speed of a sprinter. The wobble induced by Earth is 9 centimeters per second. That's the speed of a crawling tortoise. In the early 90s, our instruments could barely detect shifts of hundreds of meters per second. We needed to measure the speed of a run from light years away. The technology improved rapidly. The spectrographs became more stable. The software became better at filtering out noise. Astronomers began pointing their telescopes at nearby, sun-like stars, hoping to see that telltale oscillation. They expected to find solar systems like ours, Jupiter-mass planets taking 12 years to complete a leisurely orbit. They prepared for a long vigil. They were wrong again. In 1995, Michel Mayor and Didier Queloz pointed the telescope at 51 Pegasi, a sun-like star 50 light-years away. They saw a wobble, but it wasn't the slow 12-year cycle of a Jupiter. It was a frantic, thrashing signal. The star was wobbling back and forth every 4.2 days. The calculation made no sense. The object causing the wobble had the mass of half a Jupiter, but it was orbiting 7 times closer to its star than Mercury is to the Sun. The surface temperature of the planet would be over 1,000 degrees Celsius. It was impossible. Gas giants form in the cold outer reaches. They can't exist that close to a star. Critics argued the data was flawed. Maybe the star was pulsating. Maybe it was a spot on the surface. But the signal was clean. Mayor and Queloz had discovered 51 Pegasi b, the first planet around a sun-like star. It was the first hot Jupiter. This discovery broke our models of planetary formation. It forced us to invent the theory of planetary migration. Planets are not static. They move. They drift. 51 Pegasi b had likely formed far out and spiraled into a fiery death dance with its host. The floodgates opened. The radial velocity Doppler method became the gold standard. Throughout the late 90s and early 2000s, we found hundreds of planets. But because the method relies on seeing a large wobble quickly, we found mostly weirdos. We found massive gas giants in short orbits. We found eccentric orbits. We found systems that looked nothing like home. The Doppler method had a bias. It was great at finding heavy planets close to stars. It was terrible at finding Earths, too light to cause a big wobble, or distant Jupiters. Orbits take too long to observe. We were mapping the monsters of the galaxy, but the quiet, habitable worlds remained hidden in the noise. To find an Earth, we needed to stop looking at the wobble and start looking at the shadow. We needed to stare at the stars and wait for them to blink. We needed Kepler. The year 2009 marked the transition from artisanal planet hunting to industrial-scale discovery. Before this moment, finding an exoplanet was a bespoke process, targeting specific stars, booking time on ground-based telescopes, and painstakingly analyzing months of spectroscopic data. We were fishing with a single line. NASA's Kepler Space Telescope changed the game by throwing a drift net into the cosmic ocean. Kepler's mission design was deceptively simple. Stare at one patch of the sky and never blink. It focused on a field in the constellations Cygnus and Lyra, monitoring the brightness of roughly 150,000 stars simultaneously. It wasn't looking for wobbles. It was looking for shadows. This is the transit method. If a planet's orbit happens to be aligned perfectly edge-on relative to Earth, the planet will pass in front of its host star once per orbit. When it does, it blocks a tiny fraction of the star's light. For a Jupiter-sized planet passing in front of a Sun-sized star, the dip in brightness is about 1%. For an Earth-sized planet, it is a staggering 0.01%, or 100 parts per million. Imagine trying to detect a flea crawling across a car headlight from 10 miles away. That was the precision Kepler required. The data that poured down from Kepler was revolutionary. It didn't just find planets, it found thousands of them. And in doing so, it revealed the second great anomaly of our galactic neighborhood. We expected to find solar systems that were somewhat like ours, perhaps a mix of rocky inner worlds and gas outer worlds. Instead, Kepler found that the galaxy is obsessed with a type of planet that does not exist in our own system. We call them super-Earths, or Mini-Neptunes. These are worlds with radii between 1.2 and 3 times that of Earth. They appear in roughly 30% to 50% of the systems Kepler observed. In our solar system, there is a massive gap in size. Earth is the largest terrestrial planet. Neptune is the smallest gas giant, and it is nearly 4 times the size of Earth. Between them lies a desert, but in the rest of the galaxy, that desert is a metropolis. It is the most populated real estate in the Milky Way. Kepler also revealed the phenomenon known as peas in a pod. In multi-planet systems discovered by Kepler, the planets tend to be surprisingly uniform in size and regularly spaced. Picture a system with 4 planets. They might all be 2.5 times the size of Earth, orbiting with periods of 5, 10, 20, and 40 days. They look like a manufactured set, ordered and precise. This contrasts sharply with our system, which is a jumbled collection of tiny rocks, gas behemoths, and icy giants with varying spacing. Why did our system skip the most common mass range? Why do we lack a super-Earth? One theory is that we did have one, or were building one, and something destroyed it. Another is that the formation of Jupiter starved the inner solar system of material, preventing Earth and Venus from growing larger. Kepler also exposed the limitations of our perspective. The transit method has a severe geometric bias. The probability of a planet transiting is directly related to its distance from the star. A close-in planet has a high chance of alignment, perhaps 10%. An Earth-like planet at 1 astronomical unit has a roughly 0.5% chance of aligning perfectly with our line of sight. A Jupiter at 5 astronomical units has a minuscule chance, less than 0.1%. Furthermore, to confirm a planet, you need to see at least 3 transits to establish a period. For a planet like Earth, that takes 3 years. For a planet like Jupiter, it takes 36 years. Kepler's primary mission lasted only 4 years before a reaction wheel failure crippled its precision pointing. This means Kepler was physically incapable of confirming a true solar system analog. It could see the Earths if the geometry was perfect, but it would miss the Jupiters every single time. This leaves us with a blind spot. We know from Kepler that Earth-sized planets in the habitable zone are relatively common. The 11 billion figure comes from correcting Kepler's biases. But we don't know the context of those Earths. Are they alone? Are they accompanied by chaotic super-Earths? Do they have a Jupiter shield? The peas in a pod architecture presents another problem for habitability. These tightly packed systems are dynamically full. You cannot squeeze another planet in between them without destabilizing the whole system. This implies that these systems formed in a very calm, convergent manner, likely migrating inward together in the protoplanetary disk. Our solar system is not full. There are vast spaces between Mars and Jupiter, and between Saturn and Uranus, where you could theoretically park another planet. This dynamic emptiness suggests a violent past. It suggests that our system was not gently assembled, but carved. The Kepler data solidified the idea that the default mode of planet formation produces systems that look nothing like ours. It produces compact systems of sub-Neptunes. If this is the standard outcome, then the events that shape the solar system were non-standard. We are forced to ask, what happened here? What cleared the inner solar system of the gas and dust that usually builds super-Earths? What kept our planets small and rocky? What kept Jupiter from becoming a hot Jupiter? The answer may lie in a specific event that occurred 4.5 billion years ago, a gravitational heist known as the Grand Tack. To solve the mystery of our solar system's strangeness, the missing super-Earths, the smallness of Mars, and the existence of the asteroid belt, planetary scientists developed a radical hypothesis. It plays out like a cosmic demolition derby. It is called the Grand Tack. The standard model of accretion suggests that planets form where they currently sit. Dust clumps into rocks, rocks into planetesimals, planetesimals into planets. But when we run computer simulations of this process for the solar system, the results don't match reality. Specifically, Mars is the problem. In standard simulations, the region where Mars sits contains so much material that the planet should grow to be 1.5 to 2 times the mass of Earth. Instead, real-world Mars is a runt, barely 10% of Earth's mass. It looks stunted, as if something stole its building blocks. Furthermore, the asteroid belt is surprisingly empty. It contains less than 0.1% of the mass of Earth. Standard models predict it should be full of debris. The Grand Tack Hypothesis proposes a violent solution. It suggests that Jupiter did not form at its current location of 5.2 astronomical units. Instead, it formed slightly closer at roughly 3.5 astronomical units. As it grew, it opened a gap in the protoplanetary gas disk. The physics of disk-planet interaction caused Jupiter to lose angular momentum and spiral inward. It migrated. In this scenario, the young Jupiter plowed through the solar system, migrating all the way in to about 1.5 astronomical units, the current location of Mars. This inward charge was catastrophic for the inner solar system. Jupiter's massive gravity acted like a snowplow. It scattered planetesimals, disrupted the orbits of early protoplanets, and compressed the material in the inner region. This explains the peas in a pod systems we see elsewhere. If Jupiter had kept going, it would have become a hot Jupiter, and our inner system would have been ground into dust or ejected. But something stopped it. That something was Saturn. Saturn formed later and further out. As it grew and migrated inward, it eventually caught up to Jupiter. The two gas giants locked into a specific orbital resonance, a 3:2 mean motion resonance, where Jupiter orbited the Sun 3 times for every 2 orbits of Saturn. This resonance changed the fluid dynamics of the gas disk around them. Instead of pushing them inward, the gap they opened caused the net torque to reverse. Like a tacking sailboat catching the wind, the two giants reversed course. They migrated outward, moving from 1.5 astronomical units back out to their current positions of 5.2 and 9.5 astronomical units. This in and out maneuver explains everything. First, the small Mars. Jupiter's inward journey truncated the disk of material at 1 astronomical unit. It ate or scattered the material that would have built a larger Mars. Mars formed from the scraps left behind. Second, the asteroid belt. As Jupiter barreled through the belt region, twice, once in, once out, it scattered most of the asteroids, leaving behind the thin, dynamically excited population we see today. It also mixed icy asteroids from the outer system with rocky ones from the inner system, explaining the compositional diversity of the belt. Third, the missing super-Earths. It is possible that a first generation of large close-in planets, super-Earths, had already formed before Jupiter arrived. Jupiter's migration could have destabilized their orbits, causing them to crash into the Sun or be ejected. Earth and Venus then formed later, from the debris of this first apocalypse. If the Grand Tack is correct, it implies that the solar system is a survivor of a specific, highly unlikely sequence of events. We needed a Jupiter to form. We needed a Saturn to form at the right time and mass to catch it. We needed them to lock into resonance and reverse course before they destroyed the habitable zone completely. In most systems, perhaps Saturn doesn't form fast enough, or perhaps the resonance doesn't hold. In those cases, the Jupiter continues inward, becoming the hot Jupiter we see so often, and the system is sterilized, or perhaps no giant forms at all, and the inner system grows unchecked into a crowded system of super-Earths with no gas giant shield. This hypothesis paints a picture of a chaotic, dynamic early history. It suggests that calm solar systems like ours are not the default state, but the result of a delicate gravitational balance. But there is a catch. The Grand Tack is a simulation. It is a mathematical story that fits the facts, but we cannot travel back in time to verify it. To test if this kind of architecture is truly rare, we need to find other systems that look like ours. We need to find cold Jupiters and cold Saturns in wide orbits around other stars. And this brings us back to the observational problem. The transit method, Kepler tests, cannot find these planets because they take too long to orbit. The radial velocity method struggles because the signals are slow and weak. We are missing the data point that confirms or denies the Grand Tack's ubiquity. We need a new way to see, a way to measure the architecture of a system without waiting for a shadow or a spectral shift. We need to watch the stars move across the sky. We have relied on shadows, transits, and rainbows, Doppler spectroscopy, for 30 years. But there is a third way to find a planet, and it is the most intuitive of all. Just watch the star move. This is called astrometry. It is the oldest branch of astronomy, dating back to Hipparchus, cataloging star positions in ancient Greece. but using it to find exoplanets requires a level of precision that has only recently become technologically possible. The physics is identical to the Doppler method, but the observational perspective is different. Remember the barycenter, the center of mass between a star and a planet. As a planet orbits, the star executes a small orbit of its own around this point. In the Doppler method, we measure this movement along the line of sight, towards or away from us. In astrometry, we measure the movement across the plane of the sky. We are looking for the star to trace a tiny ellipse or circle against the background of more distant stars. Why is this better? Because the magnitude of the astrometric signal scales differently than the Doppler signal. The Doppler signal, radial velocity, depends on the speed of the star. A planet in a close orbit makes the star move fast. A planet in a distant orbit makes the star move slow. This is why Doppler is biased toward finding hot Jupiters. The signal strength decreases as the planet gets further away. The astrometric signal depends on the physical displacement of the star. Imagine a seesaw. If you have a heavy kid, star, and a light kid, planet, the heavy kid has to sit close to the pivot, barycenter, to balance. If the light kid moves further back on the seesaw, larger orbit, the heavy kid must also move further back to maintain balance. Therefore, a planet in a distant orbit causes a larger wobble in the star's position. This is the golden key. Astrometry is biased in favor of finding long-period, wide-orbit gas giants. It is the perfect complement to the Doppler and transit methods. While they struggle to see the outer solar system, astrometry thrives there. Let's put numbers to it. A Jupiter mass planet at 0.05 astronomical units causes a massive Doppler shift, but a microscopic astrometric wobble because the physical displacement is tiny. A Jupiter mass planet at 5.2 astronomical units, our Jupiter, causes a slow, small Doppler shift, 12 meters per second, but a significant astrometric wobble. From 10 parsecs, 33 light-years away, our Sun would appear to wobble by about 500 micro-arc seconds over a 12-year period. 500 micro-arc seconds. What does that mean? An arc-second is 1/36th of a degree. A micro-arc-second is 1/1,000,000th of that. To visualize 500 micro-arc-seconds, imagine standing in New York and trying to see a quarter on the surface of the moon, or trying to measure the growth of a human hair from 10 kilometers away. This extreme precision requirement is why astrometry has lagged behind other methods. The atmosphere of Earth acts like a blurry lens. Turbulence blurs starlight, making ground-based astrometry nearly impossible for planet hunting. The twinkle of stars is actually the atmosphere distorting their position and brightness. To reach micro-arcsecond precision, we had to leave the atmosphere. We had to go to space. Astrometry offers another massive advantage. It reveals the true mass of the planet. The Doppler method has a flaw known as the Sinai ambiguity. It only measures the velocity vector pointing at Earth. If a system is tilted face-on relative to us, the planet orbits in circles, but the star doesn't move towards or away from us. The Doppler signal is 0. If it's tilted at 45 degrees, we only see a fraction of the motion. This means Doppler measurements only give us a minimum mass. That Jupiter we found might actually be a brown dwarf or a star seen from a steep angle. Astrometry sees the full two-dimensional motion of the star on the sky. It can determine the exact inclination of the orbit. This allows us to calculate the true mass of the planet. This is critical for distinguishing between a heavy gas giant and a light brown dwarf, or between a super-Earth and a Neptune. Furthermore, astrometry does not require the planet to transit. Transits are rare, less than 1% for Earth-like orbits. Astrometry works for every star that has a planet, regardless of alignment, unless it's perfectly edge-on and moving only radially. But even then, we can combine methods. So, if astrometry is the holy grail for finding solar system twins, systems with distant cold Jupiters, why haven't we done it yet? Because building a machine capable of measuring angles that small is one of the hardest engineering challenges in human history. For decades, we tried. The Hipparcos satellite in the 90s mapped 100,000 stars but lacked the precision to find planets. NASA proposed the Space Interferometry Mission, SIM, which would have been capable of finding Earths, but it was canceled due to budget cuts and the success of Kepler. Europe, however, persisted. The European Space Agency, ESA, designed a successor to Hipparcos, a machine made of silicon carbide operating at absolute zero stability, designed to map not just thousands, but billions of stars. They built Gaia. In December 2013, a Soyuz rocket roared into the sky from French Guiana, carrying a toroidal masterpiece of engineering to the L2 Lagrange point, a gravitationally stable parking spot 1.5 million kilometers from Earth. This was Gaia, the surveyor of the heavens. Gaia is not a telescope in the traditional sense. It doesn't take pretty pictures of nebulae to put on coffee mugs. It is an astrometric machine designed with a singular obsessive purpose: to measure the positions, distances, and motions of stars with unprecedented accuracy. Its goal was to create the definitive 3D map of the Milky Way. To achieve this, Gaia employs a technique remarkably similar to how human eyes perceive depth: triangulation. It has two telescopes pointing at an angle of 106.5 degrees apart. As the spacecraft spins, the same stars pass through the field of view of both telescopes. By measuring the precise timing of when a star hits the detectors in field A versus field B, Gaia can calculate the relative angles between stars. But Gaia doesn't just sit still. It scans the sky continuously. Over its 5 and now 10-year mission, it observes each of its target stars roughly 70 to 100 times. As Gaia orbits the Sun, it views the stars from different locations in Earth's orbit, a baseline of 300 million kilometers. This allows it to measure parallax. Parallax is the apparent shift of a foreground object against a distant background. Hold your thumb out and close one eye, then the other. Your thumb jumps. Gaia measures the jump of stars against the background of distant galaxies, quasars. The size of this jump tells us the distance to the star. Before Gaia, we knew precise distances to only a few thousand nearby stars. Gaia has given us distances to over 1.5 billion. The precision is mind-bending. For the brightest stars, Gaia can measure positions to an accuracy of 7 micro-arcseconds. To put this in perspective, Hubble Space Telescope resolution, approximately 0.05 arcseconds. Gaia precision, approximately 0.000007 arcseconds. If you were in London, Gaia could distinguish between the two headlights of a car in Chicago. Or more famously, it could measure the width of a coin sitting on the surface of the Moon from Earth. This extreme sensitivity makes Gaia the ultimate planet hunter, but in a way that requires patience. Remember, to find a planet via astrometry, you need to watch the star trace its tiny elliptical path around the barycenter. This path takes time to complete, one full orbital period of the planet. If you are looking for a Jupiter, 12-year orbit. You need to watch for a significant fraction of those 12 years to confirm the curvature of the path. Gaia's data is released in batches. DR1, 2016, preliminary map, DR2, 2018, a revolution. 1.3 billion distances. It revealed the history of galactic collisions, stellar streams, and hypervelocity stars. DR3, 2022, the first hint of non-single stars. This release focused on binary star systems and included a catalog of non-single star candidates, identifying wobbles that weren't just parallax. But the real treasure for exoplanet science is hidden in the time series data. Until now, Gaia has mostly published the average positions and motions of stars. To find planets, we need the residuals, the tiny deviations from the straight-line path that the star makes over time. We need to see the wiggle. The signal is incredibly subtle. A star moves across the sky, proper motion. It loops due to parallax, Earth's motion, and superimposed on that is the tiny wobble of the planet. Disentangling these three motions requires a mathematical tour de force. You have to subtract the Earth's motion perfectly. You have to account for the stability of the spacecraft, thermal expansion, and even the gravitational bending of light by Jupiter and Saturn in our own solar system. Despite these challenges, the dam is beginning to break. In the DR3 release, astronomers identified the first batch of confident astrometric planet detections. These weren't just statistical anomalies. They were confirmed massive objects tugging on their stars. This brings us to the proof of concept. We didn't just find random wobbles. We found specific massive worlds that validated the method and gave us a glimpse of what is coming. We found the hidden giants. The headline discoveries from Gaia's third data release were not Earth's. They were monsters. Buried in the terabytes of telemetry were the signatures of two particular systems that proved Gaia's capabilities beyond a doubt: Gaia 4b and Gaia 5b. These planets are significant not just because they exist, but because of what they are and where they are. They represent a class of planet that has been notoriously difficult to detect with other methods. Long-period massive gas giants orbiting low-mass stars. Let's look at Gaia 4b first. It orbits a star not unlike our Sun, but slightly cooler. The planet itself is a behemoth, estimated to be roughly 12 times the mass of Jupiter. This places it right on the boundary between a planet and a brown dwarf, a failed star. It orbits at a distance of roughly 3 to 4 astronomical units, similar to the distance of the asteroid belt in our system, and takes several years to complete a circuit. Gaia 5b is even more extreme. It orbits a red dwarf star, a star much smaller than the Sun. Yet the planet is a leviathan, weighing in at approximately 21 Jupiter masses. This finding is a challenge to planet formation theories. Standard accretion models suggest that small stars should have small disks, meaning they shouldn't have enough material to build such massive companions. Gaia 5b is a super Jupiter that shouldn't be there. The detection of these worlds was a rigorous process. The Gaia team didn't just see a wobble and declare a planet. They had to filter out millions of false positives. Instrument noise, binary stars, background quasars, and even star spots, large sunspots, can mimic the astrometric signal of a planet. To confirm Gaia 4b and 5b, astronomers used ground-based telescopes to follow up with radial velocity measurements. The Doppler data matched the astrometric data perfectly. The star was wobbling in velocity exactly as Gaia predicted it was wobbling in position. This cross-confirmation was the smoking gun. It proved that Gaia's astrometric sensitivity is real and that it works for substellar companions. What did these discoveries teach us? First, they showed that massive planets can exist in wide orbits around diverse stellar types. Second, they demonstrated that we can determine the true mass. With radial velocity alone, we might have underestimated the masses of these objects due to orbital inclination. Gaia pinned down the inclination, revealing their true heavy nature. Third, they hinted at a population of dark companions. These objects are too faint to be seen directly and too distant to transit, but their gravitational footprints are unmistakable. But Gaia 4b and 5b are just the tip of the iceberg. They are the easy detections, the heaviest planets causing the biggest wobbles. The real revolution will come when we dig deeper into the noise to find the lighter planets, the regular Jupiters, the Saturns, and perhaps even massive super-Earths around nearby stars. The importance of finding these cold giants cannot be overstated. Remember the Jupiter shield hypothesis? To know if our solar system is rare, we need to know the frequency of Jupiter analogs. Kepler told us about Earth-sized planets in close orbits. Doppler surveys told us about hot Jupiters and eccentric giants. Gaia will tell us about the quiet giants, the ones that sit patiently in the outer system, potentially shepherding habitable zones. If Gaia finds that cold Jupiters are common, it increases the probability that shielded, stable, habitable zones are common. If it finds they are rare, it suggests the solar system is a diamond in the rough. We are currently in the lull between data drops. The scientific community is honing its algorithms, building pipelines of code designed to ingest the next Gaia release and spit out planet candidates. They are preparing for a flood. The next release, DR4, will not just add more data. It will fundamentally change the nature of the dataset. It will provide the individual epoch data, the time series positions for every star. This will allow independent teams to hunt for planets, rather than relying solely on the Gaia Consortium's internal analysis. The predictions for what we will find are staggering. The future of exoplanet science has a date, and it is roughly December 2026. This is the anticipated window for Gaia Data Release 4, DR4. While the previous releases were significant, DR4 is the moment astronomers have been waiting for since the mission was conceived. It will contain 66 months, 5.5 years, of continuous observation data. Why is this duration critical? Because to confirm a planet via astrometry, you ideally want to see it complete a full orbit, or at least a significant curved arc of its orbit. 5.5 years is enough time to capture the full orbital motion of planets out to about 3 or 4 astronomical units, roughly the distance of the asteroid belt or a warm Jupiter. It is half the orbital period of a true Jupiter analog, 11.8 years, which is sufficient to detect the curvature and characterize the orbit with high confidence. 2 astrophysicists, Caleb Lammers and Joshua Wynne, recently published a landmark paper attempting to quantify exactly what DR4 will deliver. They didn't just guess, they built a synthetic galaxy. They took our current knowledge of exoplanet occurrence rates from Kepler and Doppler surveys, combined it with the known performance of the Gaia instrument, and ran a massive simulation. Their conclusion? A tsunami is coming. They predict that Gaia DR4 will reveal approximately 7,500 new exoplanets. To put that in context, Humanity has discovered roughly 6,000 exoplanets in total over the last 30 years. Gaia is poised to double the known catalog of planetary systems in a single data dump. But it's not just about the number, it's about the type. The vast majority of these 7,500 planets will be gas giants, Jupiter and Saturn mass, in intermediate to wide orbits, 2 to 6 astronomical units. This is the exact population that Kepler missed. This is the exact population that Doppler surveys struggle to find efficiently. Gaia will fill in the missing piece of the puzzle, the outer architecture of planetary systems. The simulation suggests a specific breakdown. Approximately 3,000 detections will be around Sun-like stars. Approximately 4,500 detections will be around M-dwarfs, red dwarfs. This M-dwarf population is particularly interesting because red dwarfs are lightweight, often 10 to 50% of the Sun's mass. A planet of a given size causes a much larger wobble. This means Gaia will be sensitive to smaller planets around these stars, perhaps down to Neptune or even super-Earth masses in wide orbits. Furthermore, the volume of space Gaia searches is immense. Kepler looked at a pencil beam cone extending 3,000 light-years deep. Gaia looks everywhere. It will find planets around the brightest, nearest stars, the ones that are easiest to follow up with other telescopes. And this is just DR4. The Gaia spacecraft continued operating well past its nominal 5-year lifespan. It gathered data for over 10 years before its fuel reserves began to dwindle, and the mission wound down operations in 2025. The final complete dataset, Data Release 5, DR5, is expected in the early 2030s. DR5 will span 10.5 years of observation. This doubles the time baseline again. With a 10-year baseline, we can detect planets with periods of 20-plus years. We can see true Saturn analogs. The sensitivity increases drastically because the astrometric signal, the size of the wobble, grows with orbital distance. A planet at 10 astronomical units causes a bigger wobble than one at 5 astronomical units, provided you wait long enough to see it. Lammers and Wynn's prediction for DR5 is nothing short of astronomical. They estimate it could yield up to 120,000 exoplanet detections. 120,000. If this prediction holds, Gaia will go down in history not just as a star mapper, but as the greatest planet hunter ever built. It will transition us from the era of collecting stamps, finding individual planets, to the era of big data, comparative planetology. We will be able to say with statistical certainty exactly how common solar system-like architectures are. We will finally know the answer to the Jupiter question. Scenario A. We find 20,000 systems with a cold Jupiter at 5 astronomical units. Conclusion. The solar system architecture is common. Life could be everywhere. Scenario B. We find that cold Jupiters are extremely rare, comprising less than 1% of systems. Conclusion. The shield required for life is a luxury item. The solar system is a rare oasis, but Gaia cannot do it alone. To find a true Earth 2.0, we need to combine its power with another hunter. We need to merge the wobble with the shadow. We have arrived at the final frontier of exoplanet science, synthesis. For decades, the community has been fragmented. The transit hunters, Kepler, TESS, looked for shadows. The radial velocity teams, HARPS, HIRES, looked for speed wobbles. The microlensing surveys looked for gravity magnifying light. Each method revealed a different slice of the pie, but none could see the whole picture. Kepler saw the inner systems. Earths, super-Earths. Gaia sees the outer systems, Jupiters, Saturns. The Holy Grail is to find the same system with both methods. This is the synergy that will define the next decade of astronomy. NASA's TESS, Transiting Exoplanet Survey Satellite, is currently scanning the entire sky, looking for transiting planets around bright nearby stars. These are the exact same stars that Gaia is monitoring for wobbles. Imagine a specific star, let's call it Target X, located 50 light-years away. TESS observes Target X and detects a small periodic dip in light every 300 days. It confirms an Earth-sized planet in the habitable zone. This is a monumental discovery, but it leaves questions. Is this Earth safe? Is the system stable? Gaia looks at Target X. It sees no wobble corresponding to the Earth, too small, but it detects a clear 12-year oscillation corresponding to a Jupiter-mass planet at 5 astronomical units. When we combine these two data points, the picture snaps into focus. We have an inner rocky world and an outer gas giant. We have a solar system analog. This combination, transit plus astrometry, is the key to measuring the true solar system frequency. We don't just want to know if planets are common. We want to know if our arrangement, the arrangement that produced Shakespeare, the internet, and you, is common. The implications of this synthesis extend to the search for biosignatures. In the 2030s and 2040s, humanity will launch the next generation of flagship telescopes, such as the Habitable Worlds Observatory, HWO. These machines will be designed to directly image Earth-like planets and analyze their atmospheres for signs of oxygen, methane, and water. Telescope time on these billion-dollar machines will be the most precious resource in science. We cannot waste it looking at random stars. We need a target list. Gaia and TESS will provide that list. Gaia will tell us, look at this star. It has a Jupiter shield. It has a stable dynamic environment. It is a calm system. TESS, or radial velocity surveys, will add, and it has a rocky planet in the habitable zone. Those are the stars we will point the HWO at. Those are the stars where we will look for the blue pulse of an ocean. But what if the answer is silence? What if Gaia DR4 and DR5 reveal that the cold Jupiter is a statistical ghost? What if we find that 99% of systems are either chaotic swarms of super-Earths or desolate wastelands ruled by migrating hot Jupiters? Then we are faced with a profound philosophical realization. It would mean that the formation of the solar system required a sequence of events so precise, so balanced, and so rare. The right metallicity, the right disk mass, the right timing of Jupiter's formation, the saving grace of Saturn's Grand Tack, that we might be effectively alone in our corner of the galaxy. It would confirm the rare Earth hypothesis, not necessarily that life is rare. Microbes might be common on the moons of those infinite gas giants, but that complex technological civilizations require a level of planetary stability that the universe rarely provides. Conversely, if Gaia reveals that every 10th star harbors a quiet Jupiter and a stable architecture, then the galaxy is not a wilderness. It is a garden. It means that the conditions for long-term evolution are standard features of star formation. It means that when you look up at the night sky, you aren't looking at nuclear fire in a void. You are looking at 1 million potential homes. The data is already on the hard drives. The satellite has done its work. The numbers are being crunched. Within a few years, we will know. We started this journey wondering why our solar system is so weird. We ended on the verge of finding out if weird means unique. or if we just haven't looked hard enough. The collision of data has begun. The answer is arriving at the speed of light, preserved in the tiny, frozen wobbles of a billion stars. We have traversed the history of our solitude, from the shock of the first pulsar planets to the confused architectures of Kepler's super-Earths, and finally to the precision frontier of Gaia. We learned that our solar system is an anomaly in the current data set, missing the ubiquitous super-Earths, possessing a small Mars, and maintaining a clean separation between rocky inner worlds and gas giants. We explored the Grand Tack, the violent dance of Jupiter and Saturn that may have carved out our home and saved us from a chaotic fate. We realized that a good Jupiter might be the essential shield that allows biology the time it needs to breathe. Now, we wait. The Gaia Data Release 4 is the next great leap. It promises to reveal 7,500 new worlds, unlocking the invisible population of wide-orbit giants that have eluded us for decades. It will act as the Rosetta Stone, translating the chaotic dialect of the galaxy into a language we can understand. If we find our twins out there, we will know that we are part of a cosmic community. If we do not, we will know that the responsibility of preserving this rare, fragile blue marble is even heavier than we imagined. The universe is vast, dark, and mostly silent, but we are listening. And for the first time in history, we have the tools to hear the whisper of a world just like ours. Thank you for watching. If you want to stay updated on the Gaia data drops and the future of exoplanet discovery, make sure you are subscribed. The universe is getting bigger every day,